All right, and we're go. Before we begin, any questions from last time about the syllabus or anything we talked about? Guess not. We didn't really do any math last time, I guess. So let's just jump into it. Well, with the last class that I taught, I kind of started the second lecture just talking, again, giving some general information about what we're all doing here and how to succeed and all that stuff. So I guess I'll give you guys the same speech. So this is Calculus 1. And what is calculus? Right? Why are we here? Why are we studying this? Does anyone know what it's about? Yeah?
Rate.
Rate?
Change.
Rate of change. What else? With circles? Circles, you said? Okay. Not quite. It would deal with circles and other things. Yeah?
Developing solving problem skills.
Well, pretty much every math class does that. Yeah.
Functions and limits.
Huh?
Functions and limits.
Functions and limits. Limits is actually a pretty good definition for it, and I'll explain why. Yeah.
Finding out ways by which formulas that we use and then not really come from.
Not really. We're not going to do a lot of derivation here, but again, that would be something that applies to a lot of other math classes as well. So some people mentioned it. Rate of change is one thing, but limits is actually a pretty good way to describe calculus. That's really sort of describing it on the meta level, like what is the tools that we're using. So calculus has two parts. In Calc 1, we'll mostly be dealing with the first part, which is called differential calculus. Right? So the main tool in differential calculus is called the derivative. Now the derivative is actually the limit of a certain function, which we'll get to when we get to chapter 2. Right? Now what derivatives help us do is, as someone said, helps us to measure rate of change. How fast something is moving, right? If you want to figure out how fast something is moving, calculus is the math that you would use to do it, right? If you want to track the motion of something, figuring out its velocity or how fast it's changing, or how one thing is changing in respect to another thing, not necessarily time, but usually time. Calculus is what you would use to do it. And the derivative is the guy that you would use as your tool to do that, which we'll get to in chapter 2. We're not going to see that for a while, a couple weeks maybe. Two and a half weeks maybe before we see that. But yeah, that's one of the main goals of calculus, is to measure rates of change, how fast things move, right? And if you don't know anything about science, everything changes, right? That's the law of entropy, right? Everything eventually changes, breaks down and decays, and energy is transferred from one form to another. Everything is constantly changing. We live in a changing world. We're going to want to know how things change, and through figuring out how things change, how fast they're changing, the idea is we'll be able to make predictions down the road, right? So we'll be able to plan ahead based on what we see is happening, right? So that's one of the useful features of calculus, one of the main ones, and that's a little less than half of calculus. It's called differential calculus, figuring out how fast things are going. The second part, which I didn't hear anyone mention, which is okay, is we're going to touch on that a little bit at the end. We're not going to go into depth with it. Usually Calc 2, not 209, the 202 version, would go into depth with the second part. But the second part is called integral calculus, and the main tool there is called the integral, or the antiderivative. And that is also a limit. It's a limit of a function called a Riemann sum, which again, we'll get to that. I'm just giving you a good overview here. Now what the integral helps us do is figure out area, how much space something takes up, right? And again, that can help us with a lot of things as well, right? So there are two main goals of calculus: figuring out how fast something is moving, figuring out how much space something takes up, right? Things take up space, right? And anytime we have a problem dealing with one of those two things, calculus is sort of the branch of mathematics that would deal with that thing. And there are a lot of tangential, pardon the pun, applications. We're going to talk about tangent lines all the time. Applications of it. So you'll find that, well, I don't want to spoil it because I'm going to actually mention something there. I don't want to give too much away right now. Right? How fast something is going, how much space it takes up. Now, calculus has been going on for millennia, right? Archimedes was studying calculus, right? It's not actually anything new. But most people, if you talk to them and who invented calculus, where it comes from, most people will tell you, oh, Isaac Newton, or Gottfried Leibniz. They both independently developed this machinery that we call calculus today. They didn't really invent it. They sort of formalized it. They developed a lot of the notation. They really made it streamlined. But more importantly, what they did was recognize that these two concepts that seem to have nothing to do with each other are actually connected. They're linked, right? How fast something is moving and how much space it takes up in a strange way is linked together, right? Figuring out the function for one and figuring out the function that gives us the other one, they're actually kind of the reverse functions of each other in some sense, right? And in that sense is defined specifically by what's called the fundamental theorem of calculus, which we will talk about towards the end. Well, the beginning of when we talk about integrals, we'll talk about the fundamental theorem of calculus. And it's really that theorem that bridges these two fields of study, right? Differential calculus and integral calculus, the fundamental theorem of calculus connects these two branches, right? That seem to have nothing to do with each other, right? So that's sort of calculus, and there are a lot of applications that we can get from these two things, and we're going to see a lot of applications in this class. So the difference between this class and 201 is one such difference, is that we are really going to be focusing on applications, not necessarily getting into theorems or proving things or figuring out where formulas came from. We're really going to learn just enough so that we can apply it to solve real world problems, right? And usually our problems will come from medicine, population analysis, economics, things of that sort, right? Anything where things are changing or things are taking up space. That's what we're going to want to use our calculus on. Yeah, so that's kind of the point. So if you're ever wondering what's the point of all this, that's kind of the point. At any given time, that's sort of what we're doing, figuring out how fast something's moving or how much space it's taking up, and try to figure out how we can use that to answer problems, right? That's calculus. That being said, I know a lot of you here are freshmen straight out of high school, or some of you are probably took math a long time ago. Some of you probably don't believe you're very good at math, and so on and so forth. So I also wanted to talk about what it would take to do well, the skills you really want to develop to do well in a class like this, and pretty much any math class at this level. Sure, if you're a math major, eventually you get to a point where you're going to need a lot more information, like the things that were here that I erased. That's called proof-based mathematics, right? As long as you're underneath that, there are really a few things that you need to keep your eye on to be good at math, right? You don't need a big brain, you don't need a high IQ. It might help, but it's not the only thing. So, emphasize any call it elementary math. It doesn't mean you're in elementary school, but anything that doesn't depend on proofs, we call it elementary math. That's what the math people call it. Oh yeah, this is elementary. Calculus is elementary. Now, this might seem strange to you, but really, it boils down to two things. I know that sounds crazy, but it's actually true. To be an A math student, these are the two skills you need. One, form recognition. Recognizing forms, recognizing patterns, right? That's one skill that you need. Two, algorithm execution. Now remember last time I was talking about, I also kind of pointed out a few things about how to do well in a math class, and I was talking about how the conventional advice might not be enough for the individual, right? So when someone tells you, oh, just do a lot of problems, or like that 20 push-ups example that I gave, just do 20 push-ups and you look great, right? Sometimes that's not the point. The point is, at the end of the day, these two things, right? So when I say something like, oh, just practice a bunch of problems, what do I mean by a bunch of problems? I mean practice enough problems for you to gain these two skills in whatever topic that you're studying, right? These are the only two things you need. Once you have these covered, you're good, right? So I'm going to actually talk about those now. Let's start with form recognition. Recognizing forms. Recognizing forms. So I think that's good news that you really only need to keep your eye on two things. And of course, there are a lot of supporting skills to these, but people kind of will catch on to those automatically. Those are kind of different. But the two main skills you need are these two things. And the good news is everyone already possesses these two skills. Yeah, everybody, even you. Everybody, right? You already have these two skills. And I am going to show you what I mean. Okay. This is the example that I used in the other class. I guess it worked well. Okay, what's this? A chair. You guys are so smart. Wow. Okay, stay right there. I'm gonna totally confuse you guys right now. What's this? How do you know it's a chair? No, really, how do you know it's a chair? These two things look totally different to me. How do you know they're both chairs? Because you recognize a pattern, there's a form to it, right? There's something that makes something a chair, right? It has a flat piece that you can sit on, a backrest. It doesn't matter if it looks slightly different, they're both chairs. You recognize the form of a chair. Now I can show you all sorts of chairs. You'll still be able to say, hey, that's a chair. Oh, but what if it's this color? It's still a chair. What if it has wheels on it? It's still a chair, right? What's the shape? Oh, it's a chair. You'd be able to tell when something is a chair. That is form recognition. You all had it. You all know that these two are chairs. I couldn't fool you, right? So, for example, how does that help you with math? Well, let me ask you something. What's that? It's called a quadratic equation. Okay, totally gonna confuse you guys right now. What's that? It's a quadratic equation still, right?
Yeah.
But it looks different. Okay, all right, totally messing with you guys, right? What's that? Okay. Okay, what's that? Okay, with you guys. All right. Why? What's that? Okay, okay. What's that? That's a cubic equation, right? In particular, it's not a quadratic equation, right? Sometimes knowing what something is and knowing what it's not is just as important, and that's a point I'll make to you as well, right? So notice that here we can all identify these things as quadratic equations. Notice that they all look different. Some might look normal and nice and oh yeah, there's no problem. Some might look scary and crazy and you know, decimals and radicals and divisions. It's still a quadratic equation, right? How do you know it's a quadratic equation? Because there's a certain form to a quadratic equation. You know that anything that looks like ax squared plus bx plus c equals 0 is a quadratic equation, right? Now it doesn't matter what the a, the b, or the c looks like. It doesn't matter what they are. As long as they're not the variable x, and as long as your x has a second power, x has a first power, and x has a 0 power, which means you're not going to write it, it makes it a quadratic equation, right? Anything that has 3 terms, you have a variable squared, a variable to the first power, you don't have the variable, and you have 3 other numbers here, makes it a quadratic equation. And it doesn't matter what those numbers are, and because of the commutativity of addition, it doesn't matter what order I write them. I could write the c in front, it doesn't make a difference. I can still rearrange it. In this case here, the b is 0, the c is 2, the a is minus 1, right? But you still recognize it as a quadratic equation, right? Now when I went here, you guys are like, oh, that's not a quadratic equation anymore. That's a cubic, right? It's called a cubic equation because it has the cube power, third power, right? So now, knowing that something is a quadratic equation is useful, and I'm going to explain. Of course, you guys all know this, so I'm not saying anything weird here. We've all seen quadratic equations before in algebra class. Right? So, knowing that something is a quadratic equation gives us a bunch of options to solve them, right? Right? So if you know you're faced with a quadratic equation, what are some options that you have?
The long, the short.
Let's say I give you this equation, you recognize, hey, that's a quadratic equation, and I tell you, solve this equation. What can you do? Yeah? Right? One option is you can factor and use what's called the zero factor property, right? So you bring everything to one side, make this side 0, factor this side, and then set each factor equal to 0, solve for x. What's another option that you have?
Using the quadratic formula.
Right, there's something called a quadratic formula. Right, there's actually a formula that helps us solve that quadratic. Any other options? Yeah?
Completing the square.
You can complete the square. Right, which is, completing the square is kind of how this guy's derived. They're kind of the same thing, technically speaking. If you complete the square on a form like this, the result will be the quadratic formula. But yeah, these are three basic ways that we can attack this equation. These three are an example of algorithms. Right? An algorithm is the sequence of steps that you take to accomplish a certain purpose, right? And now, of course, the nice thing is, everyone knows how to follow an algorithm. That's great, right? I assume you all dressed yourselves this morning, right? You know how to put on your clothes. You know that your socks go on before your shoes, right? You know how to, if you can cook, you know how to follow a recipe. You know how to make your way to class. You know how to go up the stairs, make a left or make a right. Although some people are walking around. Well, it's the building design is weird, right? But you can follow an algorithm, right? Most of you can follow a GPS. Most of you know how to use a cell phone. Most of you can actually follow a sequence of steps to learn to do something, right? Pretty much everyone in this class. But the mere fact that you're sitting here means you can do that, right? So what happens is, when you see something like this on a math test, and I say, boom, solve this equation, there are two main phases that you would go through. First, you have to recognize the form. You have to say, hey, that's a quadratic equation. Once you recognize that form, you automatically have a list of options of algorithms that you can apply to that form, right? Now, the options might vary between the kinds of equations. For example, the factoring option can actually work with a cubic, right? And it can work in general. However, something like the quadratic formula and completing the square can only work with a quadratic equation, meaning that options 2 and 3 would not work here, right? Okay. Now, as I mentioned, let's talk a little bit more about option 3. We knew that that was a cubic. In particular, it was not a quadratic equation. So let's talk about another form. This guy. What's this? It's a table. In particular, it's not a chair. Right? Everyone with me so far? Okay. Now, these two are chairs. They look very different, but they have a certain form that I can recognize. Now, once I know that it's a chair, I automatically have a certain number of options. I can sit on the chair, right? And if it has wheels, I can roll on the chair. I have certain options that if it's a chair, I can do with it, right? Now, this is not a chair. This is a table, right? And that's a table, and that looks very different, but I know it's a table, right? Now, sometimes, depending on the object, even though this table is not a chair, sometimes I can treat it like a chair. I can sit on this table if I want to. Technically, it's not a chair, but I can use it as a chair, right? So sometimes it's important to not only know what a form is, but what a form isn't, and other times it's important to know, hey, there's a certain form that's really not this thing, but I can use it as this thing. What do I mean by that? Well, you might see something like, let's get rid of this. At some point in algebra class, your professor probably gave you something that looks like this and expected you to know how to solve it, and he only told you about quadratic equations. It's so unfair. And he put this on the test. Now, what kind of equation is that? I know what it's not. It's not a quadratic, right? Because the power is not 2 and 1 and 0, right? The power is a 4 and a 2 and 0, right? So it's not a quadratic. It's what we call a quartic equation. You don't have to know the name. It's not important. It is important, though, that you recognize it is not this, right? It's something else. However, it's sufficiently nice that I can kind of use this form to talk about that. So for example, if I don't think of the variable as x, but I think of the variable as x squared, so now, if I just think of this as a variable, right? Like call this y or something else, then it would have the form of a quadratic equation, even though technically it's not. But I can use it as a quadratic equation. I can actually do that with this, right? Because once you learn this form and you really start to get used to this form, one thing you realize is that the highest power is actually double the second highest power, right? This is a 2, that's a 1. This is a 4, that's a 2. So even though it's not a quadratic, I can treat it as a quadratic because the form is similar enough, right? I could have something else like this is a 6, this is a 3, right? That's not a quadratic, but I can treat it as a quadratic, right? So because it has a certain form, I can look at it that way. So when you are practicing a lot of problems, right? The point of it is not just to get through the homework so you don't lose points. The point is you're trying to develop these two skills, right? One, you're trying to recognize form, right? So you're going to practice enough problems so that no matter how ugly your professor makes something look, you'd be able to say, ah, that's this kind of equation. That's this kind of expression, right? And once you know what kind of expression it is, you should automatically have a list of options that you know that you can attack that expression with, right? And you should know, well, if I have anything that has this form, no matter what the A, B, and the C look like, no matter how ugly it looks, no matter how scary the professor makes it look, right? If it has this form, I have these three options, right? If it does not have this form, then I don't have all those three options, right? So for example, on this one, I might have option 1, but option 2 and 3 just won't work, right? So if I'm given this, I would never think of using the quadratic formula because it's not a quadratic, and I can't rewrite it to look like a quadratic, right? It's not the right form, right? So your goal when you're doing your homework and you're practicing math and you're studying, you're really after two things. How many problems should you practice? Enough problems so that you recognize the form that you're working with and what algorithms go with those forms, right? And as long as you can see that, no matter how something looks on the surface, right? Once you get to that point, you've practiced enough problems, right? The whole point of practicing problems is to get into this this state where you kind of see everything in their most basic elementary forms, right? So if I look at this, or 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 I look at this, I'm really seeing this. There's something in the back of my mind that has this thing pegged to all these guys, right? So once I know how to deal with this, I automatically know how to deal with those guys, right? So you might see something like, for example, not a crazy example, I'm just illustrating the point. see something like that, and I might ask you to expand that, for example, right? Now you look at that and you're like, holy crap, that looks so scary. You know, there's a square root and there's a cubic under here, and there's -7, there's a cube root of 9. That's not even a nice number, right? It looks really scary, right? But when you look at that, what do you actually see? Yeah?
A minus B squared.
Well, plus, right? A plus B all squared, right? When you look at that, don't look at and see the craziness. When you look at a problem or an expression, what you're looking for is the form, right? I don't care what the actual individuals are at the moment, right? When you approach a problem, you look at it from a global perspective. You look from the outside and then you go inside, right? Try to figure out what kind of object is this thing that I'm looking at. Is there a nice form that can fit right above it, right? That A is just this guy here, right? And that B is just that guy there, right? It doesn't matter how ugly it looks or how it looks. Once I know how to deal with this form, which I do, what is this, by the way? Once I know how to expand that, I automatically would know how to expand anything that has that form, right? Doesn't matter what it looks like. I'm going to take this guy, put it here, this guy, put it here, this guy, put it here, this guy, put it here. Put a power on that, put a power on the last one. Now what's going to happen is, I see this all the time in math class, students get afraid of how something looks. They see something and they freak out, like, oh my God, and their brain can't process it. It's because you're looking at the wrong thing. You're starting at the micro level when you should be looking at the macro level. The first thing you look at when you see a problem, what you should be looking for is a form. There's always a general form that will apply to that thing. And once you identify the form, you need to know what algorithms go with that form and how to apply those algorithms. Now, as far as form is concerned, the supporting skills that you might need to help you with recognizing a form . One, you need to know your algebra. Right? Algebra is the basics. That's where you learn the forms and you learn a bunch of algorithms to go along with them, right? Now, having gone through algebra class, you would have known what a quadratic equation looks like. You would have known that form. You would have learned that form. At some point, you had to learn the form, right? At some point, when you were a baby, you didn't know what a chair was. At some point, someone had to tell you, that's a chair, right? Algebra is where you learn what the forms are. You need your algebra, and this is one of the reasons why, right? So when things look scary and crazy and unfair and your world is going black and you get test anxiety and your palms are sweating, to recognize that it's really not that big a deal, you need your algebra. Now what you need from algebra is going to be your formulas. So at some point you need to remember your formulas and definitions. There are a lot of times I'm going to tell you about definitions. I'm going to define something. And the point of me defining it is not just to waste time writing it on the board. It's for you to, I'm describing the form to you. I'm telling you what something is, right? How it functions. So that when you see it in different contexts, you recognize, oh, that's this kind of thing, right? So you need your formulas, your definitions, and you need algebra, because that's where that's where you learn forms from. Algorithms, well, that's pretty much all algebra, right? Now, in algebra class, you learn steps to do this, right? Completing the square, it's a phrase, but it's actually a list of steps. There's an algorithm that you go through, right? You factor out the leading coefficient. You take half of this and you square it and you make that and you combine it. There's a whole process to go through to complete the square, right? That, again, you learn from algebra. Algebra not only tells you about forms, algebra is where you learn how to deal with a certain form, right? Now, in calculus, calculus is going to have its own forms and algorithms, but it's really just applying algebra, right? The sequence of steps are going to be just like applying them in algebra. Your goal is going to be to figure out, because when we really get into this thing, I'm going to throw all sorts of functions at you, and they're going to look crazy, and they're going to look really weird. The goal for you is you need to practice enough problems so that you can see forms, not the specific problem. When you look at something, you see this, right? You look at this, you see this. If you look at this, you see that. You look at this, you see that. You look at this, you see that, right? You should be able to recognize a form when you see it. That's going to be the important thing. And once you recognize the form, know what algorithm goes with that form, right? So there are tons of times when I see students apply formulas that it doesn't apply to the thing that they're applying it to. So when we get to derivatives, don't worry about what a derivative is right now. I'm going to tell you a formula to differentiate. I'll tell you what that means. Something like x squared, right? And there's going to be an algorithm or a formula that applies to differentiating something like this, right? And then on a test, you might see something like this, right? Now, what kind of function is this?
Exponential.
Oh. What's this? What kind of expression is it? What? What kind of expression is it? It's 1 times x squared plus 0x plus 0. What kind of expression is it? It's a quadratic expression. See what I'm talking about? You don't want that brain freeze. You want to be so familiar with a quadratic. It doesn't matter how it looks. You should be able to recognize it's a quadratic. A quadratic is a polynomial. So I can give you a rule that I can say. This rule applies to polynomials. What kind of expression is this one? That one might be a little hard to recognize depending on how long you've done algebra. That's called an exponential function. So this specifically is called a quadratic, but that's in a much larger family that we call polynomials. So at some point, I'm going to, for example, give you a rule, and I'm going to say, this rule applies to polynomials. And then at some other point, I'm going to give you another rule. I'm going to say, this rule applies to exponentials. And every semester, I see a student applying a rule that I told them works for polynomials, and they apply it to an exponential. Just because they see something is big here and something is small up there, the rule must do the same. No, you need to recognize the form. Here, the base is a variable, the power is a constant. It's a very different creature from which the base is a constant and the power is a variable. They're very different forms, right? So you need to recognize the difference between these two, and you just won't have these mistakes happening, right? Because you'll just know, oh, that's a chair, that's a table. I can sit on this, I shouldn't sit on that. You just know how things would operate, right? At any given time, you're going to want to be able to recognize forms because everything's going to go with a form. We're going to develop formulas and they're going to apply specifically to one class of things. And you do not want to apply it outside of that group unless I specifically say, hey, you can apply this outside of this group, right? So that's one pitfall that a lot of people have. They look at things and they're confused and they don't know what to do. It's because they can't recognize a form and they can't recognize what things go with that form, right? At the end of the day, these are the two skills you need. If you have these two skills, you'll be fine, right? So I just want to mention that. So every time we're doing something in class or you're practicing homework, make sure that you're practicing with this goal in mind, right? Right? When you see me do something on the board and you're trying to figure out why I'm doing it, what you need to identify is the form. What is the function that I'm using? And why did I do that algorithm with that function, right? Because each algorithm will go with a different thing, right? Any questions on that? You guys kind of understand what I'm saying? Especially in 205, I find that one of the biggest problems is people just get afraid. They freeze up because something looks crazy. And then they're like, you never gave us anything like that in the homework. Yes, I did. Right? If I show you how to deal with this, you should automatically know how to deal with that. It's one of those things that need to happen. Because the idea is, there are infinite variations in which something can be presented to you. I can't tell you literally every single form there is. I just have to give you a general form, and you need to be able to extrapolate it or apply it to other things in the right context. So that is your guide. If you can't tell a form or an algorithm for something, it means you haven't studied enough or you're studying wrong. Right? Now, as I said, there are many supporting skills to these two things, and that really comes down to the individual. So at some point, learning a form or an algorithm, it comes down to, a part of it depends on memorizing stuff, right? So depending on the individual, that would vary, right? How you remember is something different. People remember things different. Some people remember things visually, some people remember things, they hear it, or they write it, or they read it, right? Depending on the individual, some people like flashcards, some people don't like flashcards, some people like videos, some people don't like videos, right? You need to understand how you learn, right? Once you figure that out, you need to apply that framework to these two skills, recognizing a form, recognizing what algorithm goes with that form. Once you can do that, you're an A student, right? That's the difference. It's not the size of your brain or your IQ. Just being able to apply those two skills, which everyone has, because everyone recognized that these two are chairs, even though they look very different. You want to apply that same kind of knowledge to math class, right? And the people who can do that are the people who are successful, right? So it's not just practicing problems in a vacuum. There is a method to the madness. There's always a goal to it, right? Those two things are your goals. Now, that being said, how much time did that take? Oh. It took less time the second time around. So, that being said, I just want you to keep that in mind as you go throughout the semester, and if you take any other math class, keep that in mind as well. I know it looks very simple, but that's pretty much it. That's pretty much it. So now we're actually going to start calculus. Well, not going to start calculus. We're going to start some topics that are a review from algebra. We're not going to review everything, but we're going to review some things that are super important. For example, knowing functions and their representations. Definition. Now, a function is a very general thing. It doesn't have a particular form per se. It sort of has a particular function. A function has a particular function. Okay, so what's a function? Yeah?
A rule where you have an input and you have an output.
A rule where you have an input and an output. Right, so it's a rule, function, function, I'm defining that word, is a rule. That assigns to each element in one set called the domain of the function exactly one element in another set. This is called the codomain of the function. So the elements in the codomain that are assigned are said to be in another set called the range of the function. So that's a function. A function is a rule that connects two things, right? You look at, a set is just a group of objects, right? A collection of objects, right? They could be numbers, they could be letters, they could be anything, they could be names, right? It's a very general definition, right? So I have one group of things which I call the domain, and I'm connecting all those guys to something else in another group of things which I call the codomain, right? So I'm creating a relationship between objects, right? Now for everything in my domain, I pick exactly one element somewhere else to connect it to, right? Now once I do that, you say I have formed a function, right? And the elements that I actually select from the other group, that's called the range of the function. So for example, for a function, I can have a group of objects over here, and I'm connecting them to things over here. Each thing over here gets connected to one thing over there. Now over here, you might have other things that aren't connected to anyone, right? So this here is called the domain of the function. This group here is called the domain. This group here is called the codomain. And the list of things that are actually assigned, they're given some assignment, they are said to be in a group we call the range. Elements in the domain are called inputs sometimes. Elements in the range are the corresponding outputs. E. The domain of a function is a set of possible inputs. Or we can also call them, I'll be referring to this later on, independent variables. The range set of corresponding outputs. We might call them the dependent variables. There's going to be a topic that we do later called implicit differentiation, where knowing who's the independent variable versus dependent variable is going to be important, and I'm going to be talking about it like it's everyday language. Oh yeah, this is the independent variable, that's the dependent variable, which is this is what I mean, right? So the independent variable is kind of the guy that represents elements in your domain. The dependent variable is elements in your range. What else do we need to know about functions? Functions are sometimes given names, usually lowercase letters. So for example, I can call a function f or g or something else. Typically, but not always, typically, right, emphasis on typically, x equals the independent variable we use x to represent the independent variable and y to represent the dependent variable. Now in calculus 1 and 2, oftentimes your independent variable will change it to the letter t to represent time, right? That's very suggestive. But if you're going through algebra and precalc, usually you'll see x and y being the guys that you represent. But there's nothing special about x and y. It's just a typical thing to use. F is also typical for a function. And we write y equals f of x. So this is called f of x. And basically what this is, f is the name of the function. In other words, this rule that I made up that will connect a given x to some particular y is called f. This is a domain element, or the independent variable. And it's an input, is another way you can think of it. And this is the range element, which you can think of as the output, or the dependent variable. So when you write this notation, what you're actually saying is that there's a function whose name is f, where when I give the input x, the output is y. Right? That's what it means. When I write down y equals f of x. So this notation, don't get confused because they're brackets. It does not mean multiplication, right? When you see this, it means a function. Usually if we want to multiply two variables, we wouldn't write brackets anyway. We could just write fx. That's like f times x. But when you put the brackets here, it actually means something else. It means there's a function. I'm telling you this is definition because another thing in recognizing a form is knowing the vocabulary, knowing the language that we're speaking. So when I write something down, you should be able to interpret it and give it meaning. So you say, oh yeah, this is what's going on. What else do I want to tell you about functions? There are so many things. Okay, let's look at representations. Functions can be represented. Did I tell you what? Functions are useful for modeling the relationship between objects. In Calc 1 and 2, we deal with what's so-called single variable functions. I.e., relate one variable to one other variable. Right? So we can relate an x to a y. Right? In Calc 3, which I don't think anyone needs to take this if you're in this class, you deal with what's called multivariable functions. This relates several variables to several other variables. Right? So we're kind of going to be sitting over here, right? Single variable function. We're just relating one thing to one other thing, right? Where one thing depends on another thing. So we can say, if you passed pre-calculus, you're allowed to take calculus, right? So I'm relating your pre-calc grade to your eligibility to take calculus. However, I could say a requirement that you have to pass algebra and pre-calc in order to take calculus. So I'm relating two things is connected to this one thing, right? That would be an example of a single variable function, right? So anything that where I'm forming a relationship between two objects, we can do that with functions, right? And that allows us to throw math into the mix once we can represent something as a function. There are several ways to represent it. One mapping diagrams. There's this way that they always tell you, this machine where you see the X go in and it spits out the Y. I'm not going to draw that. This is very kindergartenish. We're going to start with mapping diagrams. right? Which I drew one for you before, right? It's basically when you write something like a group of things and you're connecting them with lines. So you form a mapping diagram. Or something like this. So these here are functions. This is called a one-to-one function. Notice that each individual in the domain connects with one individual in the codomain, right? One goes with one, right? This is called a many-to-one function, right? See that there are several guys connecting to the same guy, and that's allowed, right? At least as long as one guy connects to one guy, we're fine. You can have several people connecting to the same people, that's also fine. It's still a function. Something that's not a function would be something that looks like notice that here I have a single guy over here being connected to two things, right? Because I didn't connect him to one other guy, it's not a function anymore, right? This is called a one-to-many relation. If you want to attach formulas for this, something like a circle would be in this category, right? So if you're looking at a circle and you pick a particular x value, there could be two possible outputs. You can either get the one from the top or one from the bottom, right? So a circle is not a function, right? Whereas something like y equals x squared would be a function. Each individual x value is connected to one other y value. And anything that doesn't use up your domain is not a function either. So if I have like three guys over here, but only two of them get connected, this guy doesn't connect to anything, I'm not a function either. Right, so a function is talking about a very specific relationship. I'm connecting guys in this group to guys in another group, right? And I say that guys over here depend on guys over there. They only get picked based on what's over here. So a mapping diagram is one way to represent a function. We're not going to use that way often, but it's one that if you see it, you should recognize, hey, that's a function, or that's not a function. I did that in a second. Coordinates. You can use coordinates. So I can say something like f equals, and I can give you a list of coordinates. 1, 2, 3, 4, etc. Right? And that would define a function. Or f equals, I can write a set of coordinates where I put x, comma, f of x, such that x is in the domain of f. And I put these squiggly brackets, and that's defining a function. So if you see a list of coordinates, you can think of it as a function. 3. Another way to, you can do a numerical example, numerical representation. It basically means a table of values is one way to look at a function. So for example here, going with the above example, I can say x and y, and over here I can have 1, 2, 3, and over here would be 2, 3, 4. And this table of values is representing the same function. It's just another representation. I can list things off in a table where my domain element goes here and the guy it's connected to goes there. It's a numerical representation of a function. Meaning at any given time, if you see a table and it's a list of things, you can think of it as a function and apply things that you know about functions to that problem. Or you can have what's called algebraic representation. Meaning you're using a formula. example, f of x equals, let's say I wanted to represent this as a function. What would the function be? X plus 1. Notice that here, this is my x value, this is my y value. What is the rule that connects them? Well, if I take this and I add 1, I get 2. If I take this and I add 1, I get 3. If I take this and I add 1, I get 4. The rule here is add 1 to whatever the input is. So I can write this down. And it's the same as me writing this or that, right? For the above. And in this case, what would be the domain of the function f? What are the list of elements in the domain? 1, 2, 3. Those are the possible input values that you can have, the possible x values. What's the range of f? 2, 3, 4. Right? Those are the possible outputs or the possible y values that you can have. Right? So this is called an algebraic representation. It's basically representing a function using a formula. And of course in math, this is the one that we find most useful a lot of the time. So, there's another representation, the visual or pictorial representation. Which we call graphs, visual or graphical. So it's where we can draw things on an axis. That's how we put it. The horizontal represents what variable? The x, the domain element, the input, right? We can list them. If they're numerical, we can list them on the x. 0 starts here, it increases going that way, it counts up going that way, it counts down going this way, these side is negative. This represents the output, the y's. Counts up going positive, down goes negative. And so what can happen is I can draw a picture that represents this information, right? So let's say I wanted to draw this picture, what would that look like? Straight line, how's it going? Like this? Right? Like that way, right? Going through the 1. Now, if you don't know how to draw that, what you could do is you could take a list of values that you know the function gives you, and you can sort of start plotting them, right? So you can know that a 1 would go with a 2, and then a 2 would go with 3, right? And you get these points. 3 would go with 4. And then you can connect these dots to get the picture of your function. We're not going to do that either. We're calculus, we're too good for that, right? But back when you were just learning about functions, that would be how you do it. You start with the table of values and you go to the picture. Now the thing is, these will give you different levels of information, right? Sometimes it's too cumbersome to work with a table. You'd rather look at a picture. You just want to know, is the thing going up? Is it going down? What does it look like? How is it moving, right? And sometimes you just want a formula. I want something that I can plug into a calculator, right? And you might use this representation, right? Of course, typically, 4 and 5 are the most useful representations. So in a math class, we're going to be living here a lot of the time. I'm going to be giving you a formula, or we're going to be drawing a picture and using that to figure things out. Right? We're not going to use tables or mapping diagrams. I'm not even going to write functions like this very often, but if you do end up seeing them at some point, you should be able to recognize what that is. It's a function. Right? But this is where we're going to live a lot of the time. Graphs and formulas. Right? So those are several ways to represent functions. Functions and their representations, hence the title. So a function is just a rule that forms a relationship between objects in such a way that each object in one group is related to exactly one object in another group. If that is not true, it's not a function. And functions are all around us. So for example, we can look at something like the weather or the temperature, and we can say the temperature is a function of time, right? At this time of the day, this was the temperature. At that time of the day, that was the temperature. You can use a function to track the temperature throughout the day, where you look at your input as time and your output as temperature, right? So anything. So when you see those graphs on the news channel, it's a function, right? That's what they're doing. They're relating temperature to time, right? That's an example that you can see. Okay, enough definitions. Let's actually do a problem. So let's throw a problem out there, and we're going to use functions to help us solve this problem. It's a word problem. Yes. Love those. Okay. How many do I sell if I charge $3? So here's a situation, right? I sell hot dogs on the weekends to make ends meet, right? Now, if I charge $3 per hot dog, I will sell 50 hot dogs in a day, right? If I charge $2, I'll actually sell more. I'll sell 80 hot dogs, right? That's the situation. Okay, here. Define a function h, a hot dog function, so that h of p represents the number of hot dogs sold per day, price p. Interpret h of 3. P. Identify the domain and range of this function. C. So here's a problem. Somewhat of an economic problem. Okay, so here's the situation. You got someone selling hot dogs. They sell $3 per hot dog, they sell 50 in a day. They charge $2, they sell 80 in a day. Right? So they've been selling for a few days, and those are the average numbers. right? So now we're going to define a function to talk about this, right? And I want to interpret this particular value, right? Assuming that these are the only two prices I'll sell hot dogs for, what's the domain and range of this function? And of course, here's the real thing I want to know. What's the best price to actually charge, right? What price should I sell the hot dogs for? Should it be $2? Should it be $3? Should it be something else? What do you guys think? $3, right? Sell it for the most money possible. Is that the best option? It's not that cut and dry, is it? Right? Because if I sell it for less, I actually sell more, right? If I sell it for $3, I sell less. So going after the most money isn't going to be what's best here. But let's actually try to figure that out. Let's start with part A. So I defined a function that I'm naming h. Interpret h of 3. What does h of 3 mean? Tell me in English. What would h of 3 be for this function? What? Look at how the function is defined. Huh? No, tell me what it is. I want an interpretation, a sentence, a phrase. Yeah?
The number of hot dogs sold at price $3.
The number of hot dogs you will sell at a price of $3. Right? So I just told you how I set up this function. This is the rule that's connecting two variables, which I call h and p. Right? I'm connecting these two things. H is the number of hot dogs that I sell at a price p. So if I say h of 3, I'm talking about the number of hot dogs I sell when the price is 3. Right? Now in this case, I actually know what that value is. Right? That's what? That's actually 50. Now the thing with math is sometimes you have to jump between the math and the everyday language. You have to know how to do that. So it's very important that you can interpret something in words. You need to know what this number means. If someone says h of 3 equals 50, okay, what does that mean? It means the number of hot dogs you will sell at a price of $3 is 50 hot dogs, right? You need to be able to explain that. And you need to know that. That's how you're going to be able to decipher word problems and turn them into formulas. And so you can use form and algorithm, right? So that's h of 3. That's the interpretation of h of 3. In this case, we actually know what that value is. So far, so good. That wasn't too hard. B. What's the domain and range if these are the only two things I would solve for? What's the domain of h? And what's the range of h? Domain is 2 and 3. Right? The set of possible inputs. Now, how do I figure out who the input is? How would I know what the input is? Huh? How did I know what the input was? Yeah?
From the first question.
From this? What in this told you what the input was?
The P.
How do you know the P was the input?
Price determined.
Is that what this actually says? The price determines the number of hot dogs?
Because that's an independent variable. That's what you said.
How do you know it's the independent variable?
Because you said the price.
Not necessarily.
Because if you charge $3, then you sell 50. And if you charge $2, you sell 80. So it's the whole in and out function.
Yeah, it turns out that there are several cases, like what should be an input and an output can vary a lot. Usually the independent variable is the guy that you don't control, but it can sometimes be the guy that you do. And a lot of times you can solve a problem from either angle by thinking of one thing as the input versus the other thing as the input. But what told me the price was the input here is this expression. right? You need to learn how to read carefully. So remember I identified what a function means. Y equals f of x, it meant something, right? And we knew what the guy in the brackets meant. The guy in the brackets was your input, right? So here, because the p was the guy in the brackets, I know p is my input. I'm thinking of it that way, right? Your interpretation will have a whole different meaning depending on who's in the brackets, right? You need to identify that, right? So here, identifying h as the name of the function, and another way, when saying the function is h, that's telling me that's the output variable, right? So you read this and you're like, okay, p is the input, h is the output, right? And so I know the set of inputs would be the set of prices, which here is 2 and 3. The range would be the set of outputs would be the number of hot dogs, which are 50 and 80. Right? So if I charge 3, I sell 50. If I charge 2, I sell 80. Right? So this is the domain and range of the function. The possible inputs or prices is $2 and $3. The possible outputs are 50 and 80 hot dogs. Right? Comes from reading the problem. Okay. Any questions so far?
Did you say that the range is P or H? Yeah.
Right. The domain is the set of inputs, so the numbers in here represents the P values.
Yeah.
The range is the set of outputs, so the numbers in here represents the H values. So these here are just notation. This says domain of H, the domain of the function and the range of the function, right? But the domain is always inputs, right? So you're looking at who's the input. Those form the domain. The range is the set of outputs. Who are the outputs? And because I'm looking at a function that I call h of p, the price is the inputs, right? And the output is the number of hot dogs. Okay. Let's get to the really important question, right? What's the best price? How do we figure that out? Yes. Multiply what? Why 2 and 3?
Because of the prices that you're charging, and 50 and 80 are the amount of hot dogs that you're actually selling. So to get the total amount, you have to multiply it by 50 to get how much money you actually made that day with 2 and 80.
That would be true. That would be the case if 2 and 3 were the only prices. In problem 3, what did I say? I sort of changed things up. I'm willing to vary the price now, which means I'm willing to sell it for something other than $2 or $3. How do I figure out what's the best price? That might be a good idea. How do we find a function here? Yeah?
Maybe we can come out with a formula.
That would be a good idea. Formulas are nice. We can plug numbers in and get outputs. That would be a nice thing to do. How would we get a formula? Yeah?
You can use the range and the domain, so.
Okay. And what would we
Out
do?
of 2.
Okay. And what would you do with that information? So we know 2 points. Does that help us talk about other things? Why would you make a slope? I don't know. You don't have to guess, right? Read the problem carefully. Right? We're learning how to interpret word problems now. What's going to kind of tell me where I need to go? Ah! I know there's a linear relationship. What does that phrase mean? It's not exponential. What else does it mean?
It's just going to be
It means it's connected by a line. A straight line will connect these 2 points, right? So it means that my relationship between the number of hot dogs I sell and the price, I can think of as a straight line. So finding a slope would probably be something I'd want to do because I need the slope to find the form of a line, right? It's not because I don't know, I'm just guessing, or you know, it's algebra, so I'm guessing you need to find a slope. No, you need to know why you're doing what you're doing, right? And that's because we know it's a linear relationship, which means those 2 points are on a straight line, and then I need to know what's the form of a line. I need to figure out the slope to be able to tell you that, right? So that's where we're going to start going. So let's start there. If I were to draw these axes, what would go on the horizontal? Which variable?
Main.
Which variable? Huh?
The domain.
Right, which is what? P. P is my input here. And what would go on the horizontal? The vertical. It's the only other guy, H. Okay, so what do I know so far? When P is 2, what is my H? No?
It's 80.
It was 80, right? I erased it. Just look back in your notes. So at 2, I'm at 80. So that's 1 coordinate. At 3, I'm at what? 50. So that's another coordinate. This phrase here that tells me it's a linear relationship means these 2 points are connected by a straight line. That should be a straight line. Now I want to get to a very specific answer, right? I want to know what is the best price, right? Not a range of possible prices I could sell it for. I want exactly the best one. So a picture is not really going to help me with that. I need to do something more specific. So I need to get to that formula. And so I need the formula for this function. How would I do that? Y equals mx plus b, right? Again, so once you know something is linear, that hints to you a certain form. I know what form the formula that describes this should be. Y equals mx plus b. And what is the m?
Slope.
Right, so here I know that I'm going to use y equals mx plus b. That's the form. Right? Now once I can figure out the individual numbers in this form, I can know a bunch of things that I can do with it. Right? Now in this case, it looks more like h equals mp plus b, but whatever, it's just changing the names. Right? Now my m is going to be what? The slope. And how do I find the slope? M equals slope equals, remember a form for that, that's y2 minus y1 equals x over x2 minus x1, which in this case, just to rewrite in terms of the names, it's h2 minus h1 over p2 minus p1. What are those numbers? Well, let's label them, right? Call this p1, so the corresponding, that would be h1. Call this p2, so that would be h2. So h2 minus h1 is 50 minus 80. Over p2 minus p1 is 3 minus 2. So minus 30 is the slope. Okay, now how do I get to the equation of the line? You can plug it into this. You can also use something like the point slope form. Remember there's an equation called y minus y1 equals mx minus x1? Right, I can just plug the numbers into that, right? So here, I'm going to translate this. That's a form, but specifically here, it's h minus h1 equals m times p minus p1. Where h1, p1 comma h1 is just a point on this line, m is the slope. So that's going to give me h minus, let's pick h1, which is 80, equals m minus 30. P minus P1 corresponding to 80 is 3. This means that my H is equal to what? Minus 30P. What would that be? No, that was actually 2. Right, 2 corresponding to 80. Come on, try it. You gotta knock the rust off those rings. Don't just wait for me to tell you the answer. Actually work it out. What's the number here? You multiply this out, minus 30 times minus 2 gives you positive 60. And you're going to take this minus 80, add it to that. So you take 60 plus 80, right? So you get plus 140, right? So this is my function that represents the number of hot dogs in terms of the price, right? If I give you a price, then you plug it into this function, and I can tell you how many hot dogs you're going to sell, right? So here's the question. Do I want to know how many hot dogs I'm going to sell? What is the goal here? When I say the best price, what am I actually after? How much money? Like specifically what? The most money is what I'm after, right? What price should I sell to make the most money? That's what I'm after. So I don't really care about the number of hot dogs. What makes me the most money? That's what I'm after. So how would I get to that? So, okay, I did all of that and I got H, but H is actually not what I want. I want to know what price makes me the most money. How would I figure that out? Huh? Sure, but I want the best price. How do I know what I'm going to plug in for P? Should I plug in P equals $2, $3, $2.50, $1.50? What is the number I'm going to plug in to get the most money? How do I figure that out?
Maybe we can.
Yeah?
Try to try different inputs and say 5 by 1, or make it like a chart.
Yeah, well, there's like an infinite number of answers though. Like, how do I know which ones to pick? What is, we're going to talk about this later, but what is it called when you say the amount of money you make from a certain venture? There's a term that we can use. Any people in economics here? What's that called? Revenue, right? What I'm after is revenue, right? Profit is slightly different. Profit is revenue minus costs, right? Figure out how much money you make, what it costs for you to make it. Profit is what's left over, right? What you put in your pocket, right? Here's revenue. Let's pretend I don't pay taxes or whatever. Right? It costs me nothing to sell these hot dogs, right? This is the most money I'm gonna make, right? What I'm after here is revenue. Now, notice I need to have a goal for what the problem is I want to solve. What I want to do is I want to maximize my revenue. I want my revenue to be as large as possible. That is the goal of this whole problem. Okay, so let's start there. How do I figure out revenue? How do I figure out how much money I make?
You multiply the price by how much you sold.
Multiply the price by how much I sold, right? Remember, revenue is equal to the price times number of objects sold. If you didn't remember that, don't worry about it, we'll go over it. Right? If you couldn't figure that out, what you do is when you try to figure out a general formula for something, and you actually know what its value is at certain points, try to figure out the pattern or the form that it's taking, right? So how much money would you make if you sold 2 hot dogs? If you set the price at 2? Well, if you sell 80 things and for each of them you're charging $2, what you do is you take the 2 multiplied by the 80, right? And that will tell you how much money you're making. If you're selling 3 things and each is selling for $50, what you do is you multiply the 3 by the 50. At any given time, you're going to multiply the price by the number of hot dogs, right? So you develop this idea, right? Oh, just multiply these 2 things. In other words, what am I multiplying? What's the price in terms of our variables here?
2 80.
To me, it doesn't matter. What's
The
price?
varies.
The price varies, which means it's represented by a variable, P. What's the number of objects sold? H. Okay. Now remember, we're in single variable calculus, so we really only want to write things in terms of one variable. Can I write things in terms of a single variable here? Can I rewrite this something more useful? Yeah? Well, it's the same thing, pH.
It's divided by H, or divided by
Why would I do that?
The P I'd have to do to the other side.
P. You can substitute the H with the equation.
Right, I can replace H with this. I actually know what that H is. I figured it out before. So I can do here, this is P times my H is actually this guy right here. Which is minus 30P squared plus 140. P.
Square. How does he get this?
P times P.
Oh.
Yeah, I expanded the brackets. Algebra. So this is my function for revenue. Revenue is equal to this function. What kind of function is that? It's a quadratic. And we know a lot about that form, don't we? What would this guy look like? A parabola. What? How does it look? Like this? Concave down, someone's way ahead, but all right, so how do I draw it? How do I know how to draw this? Right, I have the negative in front of the square, so I know it's an upside down thingy, right? An inverted parabola. How do I know what points it passes through?
It starts at 140. The highest point is 140.
The highest point is 140? Why
No,
would you say
wait.
that?
We have to
So
solve
have to put
the-
an input.
What's the quickest way to solve a parabola? You guys got to remember this.
equal to 0.
Why would you equate it to 0?
And then you get the x-intercepts.
Intercepts, right? You want to graph something, intercepts are one of the first things you look for. Find the intercepts. So you're going to find the intercepts on the horizontal axis. What you do is you set it equal to 0, right? To find the x-intercepts, you set y equals 0. So basically you're going to set, p squared minus 30p squared plus 140p equal to 0. How do I solve that? Quickly. Come on, say it, don't be shy. We could factor out a p, right? Now remember, this goes back to forms and algorithm. Once I get to a quadratic, I automatically know my options. I can factor, I can do this quadratic formula, or I can complete the square, right? Factoring is pretty easier because there's a common term. So I could actually factor out a p. I would get minus 30p plus 140. And then I'd set each factor equal to 0, right? So p equals 0, or minus 30p plus 140 equals 0, in which case my p would be 14 over 3, right? So my p is either 0, or it's 14 over 3. And it's going to be upside down. Okay. Now take a guess. Which point is the point that I care about? Huh? The vertex, the highest point, right? This is the picture that represents the function for my revenue. I want to make it as big as possible. Clearly the point on this function that's the largest value is going to be the vertex. We want this. So now for a quadratic, how do I find the vertex? Minus b over 2a. There's a formula for that. Right? Again, I know form, the algorithm to find a vertex is minus b over 2a. Right, so I know p for the vertex. P must be equal to minus b over 2a. B in this case is what? 140. So it's minus 140 divided by 2 times minus 30. So that's minus 140 over minus 60. Negatives cancel. 2 to this goes. That's 7 over 3, right? Which is, 7 over 3 is what? Or I could like you with dollars and cents. Huh? $2.33. That is the best price to sell it. Right? So sell it for $2 or $3, I'm cheating myself. If I sell it for $2.33, according to this situation that I described, that's where I would make the most money. Right? So this is, now as you can see, this is kind of one of the uses of math, right? You're given a problem that's a word problem. It's a problem that you'd encounter in the real world. Your friend is telling you about his situation selling hot dogs, and you can examine the situation. You can tell him, you know what? You sell it for $2.33. He just dropped the mic and walk away. And then he goes and he makes the most money. He's like, how did you know that? You know, just like, yeah, math. You know, it's algebra, right? Now, that last problem, part C, was like really long, right? So here's a question for you. We never used any calculus here. It was an algebra problem. We didn't get to calculus. We're not going to see calculus till chapter 2. But if I were to use calculus at some point, where do you think I would have used it? To find the equation of the line, or find a formula? Where would calculus come in, if anywhere? Yeah, what do you think?
C, like the third question.
Okay, which part of C?
What do you think the best price? To predict the best price.
It's okay if you don't know the answer. You know, I'm just curious to see if anyone does. We will know the answer pretty soon. Calculus would have happened here, right? So that whole problem, all that stuff I did on these two boards, I had to erase things and put back. Calculus happened right here and nowhere else. So you understand the first day when I told you you need to be good at your algebra and your precalc, because in the grand scheme of things, the calculus is going to be happening in a very small portion of your problem, right? So the thing is, I know this formula goes with quadratics that would give me a vertex, right? But this formula actually wouldn't have worked with any other random function, right? If this thing was a cubic, right, if this was p cubed here, then I couldn't use that formula, right? That formula goes with quadratics, right? Like I have to know what formulas go with one form, right? It turns out calculus, one of the uses of calculus, in figuring out how fast something goes, I can also figure out when something is as big as possible or as small as possible. And that's going to be optimization. We're going to do that in chapter 2 as well. Right? So one use of calculus is to figure out how can you maximize or minimize something. That's going to be another use that's going to fall out of the woodwork. Right? So your calculus, wherever you need to find where something attains its maximum or minimum, calculus would be what you use, especially if you don't have a general formula. Right? If this formula was anything other than a quadratic, I wouldn't know how to find the maximum, but with calculus I actually can, and we will do that. But yeah, this is where calculus would have happened, to figure out the vertex, right? Everything else is algebra, okay? So we will pick up next time. I think we're out of time now. Pretty much exactly. We'll continue with chapter 1.1 next time. We didn't finish, so I will see you guys next class. Next class we have a quiz, of course.
I have
Oh, yeah, sure.